Okay, so I guess I already streamed for like 5 or 10 minutes and the streaming wasn't going. Uh, so I'll have to go through everything again. Nice. At least probably would be better and more nicely explained. So I'm gonna go through the exercises that are inside of this repo, which is in the stream description. I discovered this yesterday, and I think it's very interesting. There are a lot of things that I'm using when I'm writing code, but mostly because like I'm trying to write code and the compiler would complain saying, "Hey, you have to enable this extension," and then I would like blindly enable it without actually knowing what I'm doing. So I think it's very interesting to have the chance to understand what's going on. Uh, Yeah, here in the README, it suggests running a REPL, either stack or cabal or ghcad, which this command doesn't work for me. I don't know why, but anyways. Uh, I'm not going to run them because I feel like fly check or Emacs suggestions and errors are good enough for this. So we're gonna start with the first chapter, obviously, which is about generalized algebraic data types. And let's go through it because this is explained pretty well here. So we're just gonna read it with my broken English and my funny accent. So the module one is which will cover GADTs and isolation. This is very basic, and we'll see where they really shine when we come to things like constraint kinds and data kinds. Oh, sorry, wait a minute. Um, Instead of Haskell, we have the notion of a homogeneous list. That is to say, a list in which all the values are of the same type. So here, if you're not familiar with Haskell syntax, we're defining data type, which is a list that takes another type as a variable, which is a, which can be any type. And it has two constructors. This is a sum type, so it can either be a nil or a const, which takes an element of type a and then recursively a list itself of A. So this is fine, useful enough. We can, for example, write a show instance for this. So there is a class called show in Haskell, which allows us to print, turn values into strings. So this is how it's written. So there is an instance. There's a constraint here. So it's saying that A itself needs to have a show instance, and if this is proved, then we can have our show instance of a list of A's. And then we have to write the instance for each of the constructors. Not the instance, sorry, we have to write the show method for each of the constructors. So we have a show of nil, so we have no elements and we're just showing the empty representation of an empty list. Or we can have a show of counts, which has a head, which is an element of type A, and tail, which is a list of A's. So we're just showing the head, which we are guaranteed to have a show instance because we have the constraint here. And then we are appending a colon, and then we're appending a show of tail, which will recursively print the rest of the list. So here there's an example. So we have a const2, const3 nil, and when we print it with show, we get 2, column 3, column empty. Uh, what we get from a standard algebraic data type declaration, such as list, is a function for each of its constructors. By writing the list declaration above, we brought the following functions into scope, which nearly isn't really a function, it's just more of a constant value, but we have nil, which is a list of A, and then we have const, which takes an A. You can see it here, it takes an A, takes a list of A and returns a list of A. This is important to get because with GADTs, this kind of thing will be exposed more explicitly. You get the picture. We take the constructor's arguments as inputs and produce a value of the type as the output. However, we should notice some restrictions. We can mention type variables in the arguments unless they're also in the result. What does this mean? It means that this is the result, so result is list of A, and we can't have something like this. Hopefully, yeah, we get an error. Say I change A to B, and this will complain saying that we can do this. And the second, which probably not the correct error, but you get the idea, okay? Because okay. And then we can constrain the values of the input using any type class. Usually this is fine, but sometimes it's inconvenient. For example, if we know we are going to be showing everything in a list, why do we need all members of the list to be of the same type? Surely all we actually need is a guarantee that the members all have a show instance, which makes sense. So show nil is an empty element, so it's the same as before with a different name. And then we have our cons, which just says that I want a constraint that A is showable, take an A, take a show list, and return a show list. We can do this because we've broken both of the above rules. We mentioned a variable A that doesn't exist in result type. What does it mean? That we have A here, which doesn't appear here. So we're breaking the first rule. And then we're breaking the second rule because we are using a constraint, and we can't do that. So this is a rather contrived example, and better ones will emerge as we get further through the exercises. So bear with me. In order to build a data type that accurately captures a requirement, we need to generalize the notion of an algebraic data type. Luckily, a well-named solution exists, GADTs, or Generalized Algebraic Data Types. Is it algebraic or algebraic? I don't know. So we get to write a data type as this. I feel like it's something that's missing. It would be nice is rewriting our list as a GADT. So we can write data list, and then we have nil, which is a list, and then we have cons, which takes a list of A and returns, a list of A, and is obviously a list of A. So we go from here. We can quickly copy and paste this here, so we get the difference. Oh, come on. Okay. I feel like I probably have to do this. Okay, and then we can write it like this, so let's get closer. So as we can see, for this list, why is it complaining? Okay. For this list, it's just like a more verbose version. So we get more or less the same thing. We're just adding a where. We're adding the type here of the constructors, which it's more correct to say the kind of the constructors. Is it? No, it's a type signature. So nil is just a list of A, and cons is a function from A to list of A to list of A. Okay. And so we get our show list, which is a show nil and a show cons, and now it's correct. We don't get any error from the compiler because GADTs allows us to break those two rules. Notice here that we've written exactly the functions we wanted. We say that a show list is either a show nil or a show cons of some A type and some other show list. When we come to write an instance for show, we'll pattern match just as we did before. However, something is different this time. When we pattern match on A, we actually have no idea what its type is because it's not in the result type. We have no information to figure it out. We can know that A inside of a list A by looking at the type, but this type doesn't have A in it. In fact, from the available information, all we could actually know is that it has a show instance. Beyond that, it could be anything. Luckily, this is the only thing we actually need. That's the only thing we actually need. So we are writing the instance here. So it's show list. As you can see, the type of add is completely opaque. We have no idea what it is. But we know that it's showable and doesn't even need to write the constraint here in the class. So as a difference, you can see that here we needed to write show A as a constraint. We don't need it here because the constraint is inside of our constructors already. And so we write it writes the instance, which is the same more or less, except for this constraint as the one we had before. Notice that the implementation is identical to list. The only difference here is that our list's inhabitants don't have to be of the same type. As long as our type is a show instance, we can add it to the list. So here we are writing, it's very interesting, we have a heterogeneous list which has strings, integers, and booleans. The compiler doesn't complain, and we can actually show it because all of these types have a show instance. So this time you get Tom colon 25 colon true colon empty. All our types are different, but they all have a show instance, and that's enough to write a show instance for the whole list. In more technical terms, we say that A in our show const construction is an existential variable. It only exists within the scope of the constructing function. Outside of that, we have no idea what it could be. All we know about it is that what's included in the context of the GADT. When you pattern match on the constructor, as we did in its show instance, we get two variables in scope. Head, which has a construct show A to A, and tail, which is a show list. We don't know what A is. If you try to do something with it, like +1, you'll get a type error saying that we can deduce a num instance for A. If you try to call add equals add, you'll get an error saying we can deduce an EQ instance. We know nothing about this type, other than it has an instance of show. As a result, we can only call it with things that work for any show type. In practical terms, this boils down to one function, and any function built on top of it, show. All we can do with this type is show it. Once we've done that, we have a string, and we can do anything we can normally do with a string. That's it. To work with an existential variable, you have to use functions that work for all its possible types. So there's show list add. Okay, this doesn't work, obviously. That's the error. Couldn't match type A1 with A. We're saying something slightly different to what we want. We're saying that the caller gets to pick what A is. For example, I could write something like test show list, maybe int show list add. Note that int is a type that implements show. So if show list add compiled, this would work. As the person calling this function, I picked A to be int. This idea of who picks types will be covered later when we cover higher rank polymorphism. For now, we can do is show the head. Okay, yeah, I have a vague grasp of this concept. I mean, I know how it works, but I know it well enough to explain it. So I'll just leave it to the next chapters because I'm sure there will be a much better job done in the description. But yeah, the main concept is that we have this value which we don't know anything about. We don't know what it is, so we can actually use it because the compiler have no idea what to do with it. The only thing we can do it is show it because we have this constraint here. So returning the value is not possible. showing the value is possible, which is pretty clear. Okay, I guess we can try the first exercise, which are here. Cool. So I'll just go grab a beer and be back in a minute so we can start the exercises. Okay, I'm back. Got a nice cold beer. It's very warm in here these days. We got a heat wave and the temperature skyrocketed. It was like almost 40 degrees Celsius yesterday. Okay, one. Let's introduce a new class, Countable, and some instances to match. So we have a class Countable A, which takes type A and exposes a method called count, which goes from A to int. So then it writes an instance countable of int, which is id, which is a function that the identity function. So if we get an int, we just return the int and we satisfy our class. If it gets a list of a's, it returns the list of the length of the list. So this is return point free. You could write it like count x equals length x, be exactly the same. And then we have a countable bool where count it's if it's true it's 1 and if it's false it's 0. Okay, so build a JDT countable list that can hold a list of countable things. We can do this. Should be pretty easy. So we have a countable nil, which is just countable list. And now we have a countable cons, which takes a countable a constraint, an a countable cons, and returns a countable cons. Save, and we get an error. Oh, sorry, of course. So this is the constructor. We need to return the type, which is countable list. Thank you, compiler. I couldn't write any code without you. I mean, that's a lie. I can write JavaScript and it's painful. It's painful, seriously. Okay, we did the first one. Hopefully it's correct. I guess I'm pretty sure it's correct. Write a function that takes the sum of all members of a countable list once they have been counted. Okay, so this data type has no other instances, so we can't fold or map or do stuff. So, but it's not really needed. So we can write this function by pattern matching on the constructors, which I hope you're familiar with. If you're looking, we can basically write something for this and something for this, which is the same thing as writing something like count list x equal case x of countable nil. Well, there's a typo, but who cares? Countable counts. Or if you're used more to other languages, could be like count list x. Well, if x countable nil, then else, which are much worse. Not much, but this is definitely worse. This can be better. I usually tend to use this, especially with lambda case extension, which allows us to write something like equal case, if I'm not wrong. It's much nicer because we don't have to repeat the function name every time. Anyways, so if you're counting an empty list, I guess we can return 0. Makes sense. If you're counting a list which has an head element and the rest, you can just count head, which we are guaranteed to have a countable instance. And so it will return a value. And then we can add this recursive call to the rest. So we can call again count list to the tail, which is in the list. So this works. Yeah, complaints because we are shadowing these variables. So let's just call this x xs. Sorry. I guess we could fire a REPL to check if this works. Maybe you don't trust me. Let's see. Haskell 01. Add okay, no module loaded. Why is that? Is there like an import load module? This was happening. I tried this earlier, and this was happening too. It wasn't happening with Countable, but I don't think I've installed it here. Yeah, this sucks. I'm sorry. As you can see, I don't use the REPL very much, so I'm not very familiar with it. But I'm pretty sure this should work. What if I just do this? Cabal. Okay, well, I'll have to install Cabal. I don't want to do it now. Take too much time. Will it? Yeah. Who cares? It's probably that the way the project was initialized is incompatible with this. Even though they say to use StackRepl. You should be able to navigate to any of the exercise directories and run your usual commands. StackRepl. Yeah. Yeah, this sucks. Ugh. Is there ways to browse files, something? Oh, okay. Okay, my bad. Okay, cool. That works. I'm sorry, Stack. Absolutely you're right and I'm wrong. Okay. We can try doing a count list of countable counts 1. Now let's use 5. Countable counts false. Countable counts 1, 2, 3. Countable nil. And then we have to close 1, 2, 3. So this should give us 5 plus 0 plus 3. So this should get 8. And we get an error. We get an error because it doesn't know if this 5 is an int, so we have to specify it explicitly. Cool, no error, and we get an 8. Cool, cool, cool. It's working. We can move to the next exercise, which is C, which is write a function that removes all elements whose count is 0. Okay, interesting. Obviously, we can use filter to write this. So we'll have to figure out a different way. So, sorry, I was just checking my phone. Looks like Emacs is not okay. So let's go one step at a time and see if we can do this. So we have a countable. Guess if we have a countable nil, we can return empty, which is not in scope. That's weird. Empty. Sorry. We don't. No, sorry. We don't have. This won't compile anyways. Obviously, because there's no monoid instance. So what we're going to do, we can just return countable nil, obviously. So if we have an empty list, we return an empty list. Makes sense. So what if we have a non-empty list? So we want to differentiate between the case in which x is 0 or is not, x is 0 or is not 0. So you can say if count x equals 0, then we can just return a countable count of x, and then we run drop 0 on the tail. Otherwise, I guess we just return drop 0 on the tail. Do we get any error? No. Okay. Let's see if this works. So we can do a drop 0 on this. What I'm expecting is that 5 is not dropped, false is dropped, and the list is not dropped. We don't have a show for this. It sucks. So this is very inefficient, but I'm just... Oh, there's no EQ either. Well, I mean, we'll have to trust the compiler. This compiles, makes sense logically. I'm not gonna write tests or other instances. So we can count this as solved. Can we write a function that removes all the things in the list of type int? If not, why not? Well, no, we can't, because we don't know anything about A. The only thing we know is that we can count it. And by counting it, we have no way to go back to what type it was before. So this is not possible. I don't know if it makes sense. 2. Yay. Write a list that can take any type without any constraints. Okay. So we have any nil, which is just any list. And then we have any counts, which takes an A, and any list returns an any list. Which easy, it's just the same one as the one we wrote before, without the constraint. Sorry. Yeah, no error. Okay, how many of the following function can we implement for an any list? Reverse any list. Can we write it? Yes, we can, because we just take the element and we append it in reverse order to the list, but we don't care what the element is, so we can definitely write it. So this is just any nil. It's any nil, which is pretty easy. Any counts xs. So what we want to do is put this x at the end of this excess. Huh. I guess we could try to use inner function with an accumulator. Which at this point this becomes excess. Yeah. You can do this, and then if you have a go any counts access, which is an unfortunate name. Even if it's not shadowy, I just want to make this clearer. Ugh. I don't know why I'm stuck here. This is pretty trivial. Probably like stage fright because I'm streaming and I'm like worried that everyone's gonna think I can't do this anything. Uh, yeah, we can do like hmm. This obviously won't work because this is a function. So we could say that we're passing a function instead of an accumulator, which in this case is any counts x, and in this case is just the identity. So we could write go ideal s, and then go f anil f anil. Okay, this should work. We don't have any way to check though. Well, I'm pretty sure it's correct. So we are running an inner function go. Which works on our list. So it's the complete list at first and takes a function which we can use. So we're starting with ID because we're starting with with nothing basically. So if it's nil, we just apply f to nil. So if we're reversing an empty list, we're just applying ID to nil and we get back nil. If you're working with a non-empty list, you just call recursively function. With the new function, is we are counting our head, and which is a function because this is a function which takes a list and returns a list, and we're appending to our function f, which can either be ID if we are our first step, or it could be other constants if you're already deep into the list. And then we pass the rest of the list. So this should work. Pretty sure. Okay, can we write a filter any list? No, we can't, because this filter assumes that we're able to pass a function that goes from A to bool, and we can't do that because we don't know anything about A. So yeah, we can't write this. Length any list. Can we do this? Yeah, because we only care about how many elements are in there. We don't care about what these elements actually are. So if we are counting an empty list, we're returning 0, obviously. If we're counting an empty list, which we don't care about the head, just doing 1 plus length any list access. We can actually test this one. Let's see, length any list, any counts 1, any counts false, any nil. We got 2, which is correct. Good. Fold any list. Can we write this? No, we can't. Because we don't have a guarantee that our elements have a monoid implementation, which I guess we could write this. Yeah, we can write empty, but it's not very interesting, is it? We're just returning an empty list anyways. But I mean, we can write it. It's not interesting, it's not useful at all, but it's correct. Is empty. Yeah, of course, it's easy. Any nil is true. False. Yeah, this was easy. Show any list. No, again, we can't show it because there is no show of a constraint here, so we can do that. I guess what we can do is like printing some representation of the list, like only how many elements are in there. Something like any nil is a 0 or an O. And this one is gonna be a, yeah, I don't really care about this. So it's gonna be an X show access. So this one is just gonna be like X colon X colon X colon X colon 0. Not not useful at all again. But I guess it's correct. Okay, 3, 4, and 5, and oh, there are a lot of 7. There are a lot of exercises. 8, 9, and 10. I'm not sure if we're gonna do all of them today. It's already been almost an hour. I embarrassed myself a little. So let's see. Consider the following GATD. So we have a data transformable to output. So yeah, I can already see where this is going. So we have an output type variable here, but we're using input here and here. Anyways, so we have the only constructor is transform with, which takes a function from input to output, takes an input, and returns are transformable to output. And the following values of this GATD. So we have transformable 1, which is a transform with show 2.5, and transformable 2, which is transformable to string. They're both transformable to string. Okay. So which type variable is existential inside transformable 2? What is the only thing we can do to it? Well, I guess the existential variable is input, because it appears here and here, but it doesn't appear in our output. The output is this whole type. The only thing we can do to it, oh, I mean, is apply this function to it. The only thing we can do. We have this input to output. We pass it input, we get an output. Could we write in a Q instance for transformable 2? What we'll be able to check? I guess we can. And only checking the outputs. Let's see if we can do this. Sorry. I'm not sure if this is gonna work. Well, we can try. So we are writing an EQ instance for our whole transformable to output. We're gonna put a constraint that output needs an EQ type class to instance to. So what we can do now is transform with we have a function and we have an input, and this has to be equal to transform with another function, another input. And I guess we can just do fi equals fi. Do we get an error? No. Can we try this? I guess we can try it. So we can try like transform with id 3 equals transform with show 3. Reload. Why am I getting an error? Did I save? Oh. Oh, transform. Okay, sorry. Yeah, it's true. It's true. Cool. So we're passing ID and a string 3, and we're passing show and the number 3, int 3, and it's true. So yeah, we can write it. Not entirely sure how useful this is, but it works. Could we write a functor instance for transformable too? If so, write it. If not, why not? Huh, can we? I think we can. Uh, no, it's actually this. Um, okay, so functor instance says that we get a function goes from A to B. We have some structure f of A, and the result has to be f of B. So in our case, our f of A is a transformable output. Oh god, I'm dyslexic. So this function has to be something like from output to output. And this has to be a transformable output. So this is it is still a transform with. We'll have to combine our two functions here. And then it's still the input, the same input, because we can do anything about the input. So we have function g that goes from, we have g, which goes from I to O. I'm just shortening input and output. And then we have f, which goes from O to O apex, quote. So I guess we can just do this, f of g. Yeah, this works. So now we can get a transformable output changed to a transformable some different output, if it makes sense, because we're combining f and g here. 4, let's go. Here's another GDT, EQ pair, where EQ pair, EQA, EQ pair. Okay. There's one, maybe two useful functions to write for EQ pair. What is it? We have an EQ constraint, so I guess we can check if they're equal. Equal pair, which takes an EQ pair, return the bool. Yeah. Well, of course we can have the dual, like not equal pair. Yeah. How could we change the type so that A is not existential? Don't overthink it. A or EQ pair is a function EQA from A EQ pair A. Yeah, looks correct. I hope. Uh, if we made the change I was suggested in B, will we still need a GATD, or could we not represent our type as an ADT? No, we need it because we are using the constraint, which was the second rule. You tried to trick me, but I'm untrickable. 5. Oh, this is getting more complex. I feel like I'm gonna stop here. I have 5 more minutes and I want to start working on this. Yeah, let's do it. 5. Perhaps a slightly less intuitive feature of GADTs is that we can set our type parameters, in this case A, to different types depending on the constructor. Okay, so we have an empty box, we have an int box, a string box, and a bool box. Okay, bool takes a mystery box string, and string box takes a mystery box int, so they're like, it's like Chinese Russian dolls, Chinese boxes, I don't know. When we pattern match, the type checker is clever enough to restrict the branches we have to check to the ones that could produce something of the given type. Oh, okay, interesting. So if we have get int of a mystery box int and we want to get the int, we can just write this. And we don't have to pattern match with these other constructors because, yeah, they can be there. Interesting. Implement the following function by returning a value directly from a pattern match. So we have to go from mystery box string to int. So mystery box string is a string box of a string which we don't care about. And then we have a mystery box int, which is an int box of an int and something that we don't really care about. And then we just return I, sorry. That works, no error, makes sense. Write the following function. Again, don't overthink it. So if it's an int box, we return it in. This will obviously give us a warning because we're not pattern matching on everything. So wait, what happens if we pass it in an empty box? I'm curious. Well, I'm probably... Oh, of course, if it's an empty box, we just return 0. Oh, sorry, we're counting the layers. We're not counting the int value. So if you're counting the layers of an int box, you can just return 1. Yeah. Yeah. Yeah, I guess we could do some recursive stuff like using all ones plus count layers of the inner box. Doesn't make any sense. And the structure is fixed. Bool box is always on top, and then a string box, and a linked box, and empty box. So try to implement a function which which removes one layer of box. For example, this should turn a bool box into a string box, and so on. What gets in our way? What would its type be? I don't think we can do this. Can we? Because, let's see. We have a strip layers which goes from a mystery box A to a mystery box of A. I don't know, I'm just try writing it and see what happens. So we can strip an empty box. Maybe we can write this function. Int box equals I. String box equals I. I is for inner in this case. Yeah, there's a typo. I'll get an error. Of course. Of course, because now, yeah, obviously we can do this. Because now A is different for each of this function. It's unit here, it's int here, it's string here, it's bool here. So yeah, of course we can't do this. Yeah, I don't think we can do this. Okay, I'm gonna stop for now. And next time I'll go through 6, 7, and then move to the second exercise. I think I'm so bad. Well, I'll see you next time.